So I want to do a right-hand rectangular approximation, but I don't want to do a couple rectangles. I don't want to do a few rectangles. I want to do 100 rectangles, which is a lot of rectangles. So we are going to use this summation notation in order to get these large number of rectangles rather than doing what the rectangular approximation 100 times. So if I just kind of made a rough graph of this thing, just so I can kind of visualize what's going on. Here we go. Got a little curve. Whoop. And we're going from 0 to 3. So this is our 0, and then we're going to head to 3. Neat. But we're going to take this and we're going to chop it up into 100 pieces. Okay, so if we're dividing into 100 sections, we need to figure out like what's going on here. So we've got our rectangles, and our rectangle comes up with a width, and we've got the height of all of those rectangles. So the width of each one of those, the full distance is 100, but it's only going to be a 100th of that. So the width of each one is 3 over 100. Now that 3 over 100 is actually something that we're going to use in something coming a little bit later. So that is our change in our x value. So our delta x. So how far we're changing from rectangle to rectangle. I cannot stop saying triangles. Because we get that sort of repeating pattern of those things. Our first one is going to be at 3 100, and then the one after that will be at 6 100ths, the ones that we're plugging into the f of x, and then we'll do 9 100ths. So not only is that telling us how wide our rectangles are, it's also telling us where our right-hand approximation is supposed to be showing up. Now, since we're doing a right-hand approximation, we do not want to have that first value. We want our right-hand side of our rectangle to be on the curve. So we are not going to, for our first height, it is not going to be 0. Our first one is going to be that f of 3 over 100, and then f of 6 over 100, and then f of 9 over 100. So we're going to do that over and over and over again. So what's kind of happening with the pattern there is this is our first one. So this is like 3 times 1. This is our second one, which is 3 times 2. And then this is our third one, which is 3 times 3. So it's really saying that our height is going to be f of 3 I. And we use this I in sigma notation to represent the ith term. So we've got our first one, then the second one, then the third one, and the fourth one. So that I is a whole number that's counting up by 1 every time. F of 3I over 100. So that would be one of the rectangles, but we have to get 100 of them. So we've got to add them all together. So we get a summation going. Our first I value is going to be 1 because we've got a 1 here, and then it'll increase by 2, and then 3, and then 4, and then 5. And the number of times that we're going to do this is 100. So we're going to keep going until I equals 100, and then we will stop. We're not actually going to calculate those one by one. We are going to try to use those sigma formulas on the previous slide in order to figure out what this is. You see why we're not going to do this a whole lot? Ugh. So in order to figure out what's going on here, one trick that we can use is this one. So that 3 over 100, what we were doing before with those rectangles, we'd always pull out whatever the height was. That didn't really matter. We just multiplied everything by that height. So we want to pull that 3 over 100 out of the sigma. It's not doing anything. So 3 over 100, summation, and then we've got to do f of 3i. So this f of 3i, we should just plug that into our function. So that is 3i over 100 squared. I'm really nervous I'm making a mistake, so I'm just trying to like keep an eye on my key. So 3i over 100 plus just a 3. So all of that is being added. So it's got 1 in all those spots, and then 2 in all those spots, and then 3 in all those spots. But we're not going to like calculate all of those thingies. But what we can do is we can figure out what each little bit is rather than doing it all at once. We can sum all of these thingies, and then we can sum all of these thingies, and then we can sum all of these thingies. So let's do that. Because the trick I'm using there, I should show which trick I'm using. I'm using this trick that if you got a bunch of things being added inside of a summation, you can break them up into separate little bits. So let's do that. Actually, I'm going to move this over a little bit. I think I'm going to need more space. And more. So we're heading over here. Okay. So we have a summation of... And I'm not going to keep writing these things. Just assume that they're there all the time. We don't need to write them every time. So let's see. That's a summation of 3i squared over 100 minus the summation of 3i over 100. Oh, this is all squared. And then plus the Riemann sum of 3. It's just a 3. Okay. Cool. Now, just like before, we've got little summations, and each one of those little summations has a constant in it that we can take out of that summation. So let's do that next. So let's try to get those constants out of those summations. So this first one has that 3 over 100 getting squared. That's just a constant. That I squared has got to stay in there. But that 3 over 100 squared, we can take that thing out. So that is, I'm just going to keep it 3 squared over 100 squared because I don't really want to write 10,000. Okay. Then we can do the same thing with this one. So minus 3 over 100, and then the summation of just an I. Now the other one's just a 3. And so if it is just a 3, if there's just a constant in there, we can do this. We can just take whatever that constant is and then multiply it by the number of times we're doing the thingy, because it would be 3 plus 3 plus 3 plus 3 plus 3. Do it 100 times. So that last one just becomes 3 times 100. Okay. Now we get into the crazier formulas. This pink one right here, I squared. Let's see what that is. So I squared is n times n plus 1 times 2n plus 1 divided by 6. N times n plus 1 times 2n plus 1 divided by 6. So we're going to replace that with that mess. Ugh. But all of our n's are 100 because that's the number of times that we're doing this. So it is 100 n plus 1, which is 100 plus 1, so 101, plus 2n plus 1, which is 201, over 6. Why is it 6? I don't know, and I don't care. 3 squared and 100 squared. Okay, the brown one. It's the brown one. It's just an I, so that is n times n plus 1 over 2. So that's minus 3 over 100. We've got an n, which is 100, n plus 1, which is 101, over 2. Whew. Okay, and then the last thing is 3 times 100. I'm not multiplying these things together because I'm real hoping some stuff's going to start canceling here. Because I think it's time for a cancel party. Let's see. I'll use teal. All right, so what can we cancel? Right here, we can cancel this 100 and that's squared. We can also cancel the squared on the 3 and turn this into just a regular, a 2. Let's see, we can cancel these 100s. Is that it? Oh, come on. Nothing else? Gross. Yep. Yeah, that's it. So we get 3. Oh, pink. 3 times 101, 201, divided by 200, minus 3 times 101 over 2, plus 3 times 100, just over 1. Okay. Math. So by the magic of editing, I've typed that into my calculator and I got 435.015. So that's the pink chunk. And then I need to multiply that by the 3 over 100. So times 3 divided by 100, the blue part that's in front. And so my estimate after adding 100 separate triangles is 13.59045. Oof. That was, well, it was a lot, but it was less than making 100 separate triangles. Blah.